Imagine steering a car through a sudden, heavy downpour on a winding, pitch-black road. The rain is blinding, the fog is thick, and the lack of visibility turns every shadow into a potential obstacle. Human drivers struggle to navigate this chaos, and so do machines. For decades, the automotive industry managed safety by asking a relatively simple set of questions. Did a wire snap? Did a computer chip overheat? Did the software code crash? Standards like ISO 26262 were designed to ensure that mechanical and electronic components didn't physically fail. But modern autonomous vehicles introduce a completely different problem. A self-driving car can crash when every single piece of hardware is powered on, and every line of code runs flawlessly. If thick fog blinds a camera, or an algorithm correctly executes a turn but misjudges the road layout, the system fails without technically breaking down. That creates a vacuum of uncertainty. If the hardware is working, how much testing is actually required to confidently declare an autonomous machine safe for the real world? The framework that provides the answer is a standard called ISO 21448, widely known as Sotif, the safety of the intended functionality. Under Sotif, the primary challenge of modern automotive engineering has evolved. Success now depends on mathematically taming the vast, unpredictable limits of the physical environment. This diagram shows the foundational formula of Sotif. We begin with a single variable, the acceptable rate of harm. This represents the societal and legal baseline for safety, defining the maximum frequency of accidents we are willing to tolerate on public roads. To meet that societal goal, the formula equates acceptable harm to the hazardous behavior rate. This is the baseline frequency at which the autonomous system makes a dangerous physical move, like steering out of a lane. A dangerous move only matters if another vehicle or person is nearby, so we multiply that behavior rate by exposure, the mathematical likelihood that the vehicle is actually driving in a specific populated scenario when the glitch occurs. Next, we multiply by uncontrollability. This measures the exact chance that a human driver, either inside the car or in the vehicle behind it, cannot physically react in time to override the hazard safely. Finally, we factor in severity. This calculates the physical outcomes of a collision, estimating the actual likelihood of injuries if the crash happens. This complete equation provides a rigorous deductive structure. It takes the broad philosophical idea of safety and breaks it down into individual, measurable sub-requirements for sensors, cameras, and braking algorithms. By deconstructing acceptable harm into these precise probabilities, engineers transition safety from subjective guesswork into an actionable mathematical boundary. Let's apply that math to a physical simulation. This models a highly monitored hazard known as a ghost target scenario. It happens when a vehicle's autonomous emergency braking system suddenly activates without provocation, catching the human driver in the trailing vehicle off guard. This data chart reveals a counterintuitive truth derived from thousands of Monte Carlo simulations. The highest probability of a rear-end crash does not occur at top highway speeds. Instead, the risk distribution peaks heavily in the lower to mid-speed ranges. The data isolates a specific danger zone between 40 and 80 kilometers per hour. Operating in this moderate speed band accounts for roughly 70% of all rear-end collisions. The physical limitation causing this anomaly comes down to distance. At moderate city speeds, vehicles naturally maintain incredibly short following distances compared to the gaps left open on a highway. If the autonomous system perceives a false threat and engages the emergency brake, the mechanical jerk is severe. The vehicle can decelerate violently, dropping speed at a rate of up to 15 meters per second cubed. The machine applies maximum braking pressure instantaneously. The human driver behind them still requires time to perceive the brake lights, move their foot, and push the pedal. Because the physical gap was so short, the space simply vanishes before the human can react. Discovering these exact physical limits within the 40 to 80 km per hour zone allows engineers to properly tune the exposure and uncontrollability variables within the Sotif equation to protect human lives. To prove these mathematical theories hold up, we use this Poisson distribution formula to calculate target mileage. For a 95% confidence level, the autonomous vehicle must drive approximately 3 times that targeted distance flawlessly without a single incident. That requirement creates a target in the tens of millions of miles. To hit that massive number, Engineers combine physical data gathered from real-world road tests with millions of miles executed in accelerated virtual simulation runs. This rigorous standard replaces traditional engineering judgment with objective, data-driven proof. The Sotif standard provides the hard mathematical proof required to forge societal trust in the machines of the future.